Hopefully we've got a few more cameras going later. We're going to look at the chain rule. Basically, we've done a lot of these, but we're going to just expand it a little bit when we get to 2 or 3 variables. So I'm going to try and pick an example of each one of these main types. The first one I'm going to do, there's quite a lot of the questions where you've got a function in terms of, say, x, y, or x, y, z, but the x, the y, and the z are in terms of one variable, typically t, right? So an example of that type of question could be something like this. Z is equal to xy to the 4, take away x squared y. And this is a version of question 2 if you're interested. And we are told that x is t squared plus 1 and that y is t squared minus 1, which is fine. Really, the key to doing chain rule is just knowing the formulas. So you're going to be asked, so you don't need to worry about what the question is going to be. You're going to be asked to find the derivative dz by dt in these questions. And the formula for getting dz by dt is the partial derivative of z with respect to x times dx by dt plus the partial derivative of z with respect to y times dy by dt. So I think I'll put it over here because I'm pretty sure I need more room. Okay, partial derivative of this with respect to x is y to the 4, and this guy gets you negative 2x y. And then you multiply it by the derivative of x with respect to t, which is 2t, plus the partial derivative of this with respect to y, and well, that guy is going to get you 4 x y cubed, and that guy is going to get you minus x squared times the derivative of that, which is 2t. And that's pretty much the major part done. What we're going to do here is, if we can make it pretty, not that I think I'm going to do much good. This is a special case. I could pull out 2t as a common factor from here and from here. And that leaves me with a y to the 4, a negative 2xy, a 4xy cubed, take away an x squared. And I think that's as good as I can do, right? So the rules for style points are make it look like the original, kind of bending the rules on that, and factor the heck out of it, which I certainly have done. I think it was David that went and said, with the exception of maybe one question, that is totally acceptable for me and for WebAssign. Now, if you get that 1 in 10 question where they don't accept that and you're sure that this is correct, don't you just have to turn all the y's and replace them by this and all the x's and replace them by that? And God forbid they ask you to do that, because can you imagine how ugly that answer is going to look like if you had to do that? But, hopefully, if it happens at all, it will only happen once. Are we comfortable with a function with just one chain rule variable? Do you want to do another one, or do you think that's, you've seen enough of them, you're good? Your choice.
Good.
Okay, I just saw one that I'm going to do now. And if I hadn't seen this one, wait a minute, did I do this yesterday? No, it doesn't matter. I think if I did it yesterday, I certainly didn't complete it. And in this world, x is 4 sine t, y is 6 cosine t, and z is going to be 3 tan t. So far, so good? Now, I remember saying this before, so that's why this one comes back to me. Isn't this just because you can doesn't mean you should draw? And what can we do about a log of a square root? Well, can't we rewrite it as 1/2 that guy? Would you agree that's just going to be easier to deal with? If I didn't do that, I would eventually get the same answer. It might not look like the same answer, but I did get that. Now I know where this came from. Didn't we have a question like this in implicit differentiation? Remember the Z guys? That's where that came from. Okay, now I know what we've got. So this one is actually new. So let's find the derivative with respect to t. That's what they're asking us. So it's going to be the partial derivative of w with respect to x times dx by dt plus the partial derivative with respect to y times dy by dt plus the partial derivative with respect to z times dz by dt. Are you comfortable about extending the chain rule formula to 3 variables? Why 3? Because this is 3, right? If this would be x squared plus y squared, wouldn't we just have those two? Great. Now, if you differentiate this guy with respect to x, and I'm going to do that as some sidewise working. So I'm going to take this function and partial derivative with respect to x. Well, you get 1/2, 1 over, right? Derivative of log is 1 over, finishing with the derivative of the inside function with respect to x, which is 2x. That and that kind of merge together, and you end up with that guy. Are you comfortable with that? Okay. Now, back to here. This guy we just found a moment ago is x over x squared plus y squared plus z squared times the derivative of 4 sine gets me 4 cosines. I do not need to do this guy from scratch. Do you recognize a symmetric function? And so if I know what the answer for dw by dx is, wouldn't it be pretty easy to predict what the answer for the next one's going to be? Anyone want to go for it then? What would the derivative dw dy be based on you know what that one is?
Y over the x squared plus y squared plus z squared.
Great. And the derivative of that guy is -6 sine t. And of course, even although I wrote as best I could, I still ran out of room. And if you're doing the z one, would you agree it's going to be z over x squared plus y squared plus z squared? And do not scare me here. What is the derivative of 3 tan t?
3 secant squared.
Thank you. Right, now style points. Well, we really are kind of stuck with style points here. Would you agree there's not an awful lot that we can do to make this pretty? But there is something I can do. Can't I pull that guy out, the bottom? And that will leave me with 4x cosine t plus, whoops, minus, it's a minus, 6y sine of t, and finishing with a plus 3 secant squared tz. So the best I can do in style points here was pulling that out. I could leave it like that, or couldn't I just make it a big ugly fraction over x squared plus y squared plus z squared? They're both equivalent. Are we cool with that question? Okay, let's do a double one. So what do you do, or how do you deal with the fact that you may have a function where there's 2 variables? An example of that, let's pick something interesting. Yeah, this one will do. This is question 6. The function I've got is z equals the natural log of 4x plus 3y. But x is s times the sine of t. And y is t times cosine of s. Very interesting. And you are going to be asked to find two different derivatives in these situations. The partial derivative of z with respect to s and the partial derivative of z with respect to t. I'm just going to pick one of them. I'm going to pick the first one. Now, if you want to find this guy, z is in terms of x and y. So that tells me I'm going to go the partial derivative of z with respect to x times dx by ds. And then I'm going to do the partial derivative with respect to y times dy ds. Are you comfortable about that formula for this combination? Isn't that essentially the contribution that x makes to the answer, and this is the contribution that y makes to the answer? Now, if you differentiate this fella with respect to x, you get 1 over 4x plus 3y, that's what the derivative of log is, times the derivative of the inside function with respect to x, so that now becomes 4. And then if you do this guy here with respect to s, all you get is sine t. Plus, if you now differentiate this guy with respect to y, you get 1 over 4x plus 3y times the derivative of the inside function, which gets you 3. And then you differentiate y with respect to s. And when you differentiate that guy with respect to s, you get negative t sine s. Right. Okay, I need some style points here. Is there anything you can do to essentially factor out something to make this a little bit prettier? Can you see anything I could factor out here that would make this a little bit nicer looking?
1 divided by 4x plus 3y.
I think that's what I heard. Agreed? Is that what you're going to say, Maggie? That leaves me with 4 sine t minus 3t sine s. And that's just housekeeping, isn't it? We should always make things look pretty if we can. You're not going to get a heck of a lot of, most of the time, anything very pretty, you know, but it's going to look a little bit better than it did. And that's probably all you can hope for. Are we good with that one? That's week 2. Okay, let's try this one. This is a version of question 7, where our function is x to the 4, x squared y, and x is a function of s, t, and u, and y is a function of s, t, and u. And in this case, you would be asked to find the partial derivative of z with respect to s and t and u. And for no particular reason, I'm going to pick u. So the key to doing these is making sure that you've got the right formula. I'll take a volunteer. Anybody want to tell me what the partial derivative dz by du would look like in this combination? Any takers? What could you do to do dz by du?
dz dx times dx du plus dz dy times dy du.
Looks good to me. Agreed? That makes sense? The contribution to the answer with x's plus the contribution to the answer from the y's. It's actually quite a small formula. You were maybe thinking it would be bigger. Well, if you're only doing u as a variable, do you see it's only the contribution of the original variables that generates the formula? This doesn't come into effect until later. Well, if you differentiate this guy, you get 4x cubed. And if you differentiate this guy with respect to u, you just get -1. If you now differentiate this guy with respect to y, you get x squared. And if you differentiate this fellow with respect to u, you get 2 STU. And there's not an awful lot I can do to make this look pretty, but even if it's only a little, I should try it. Okay, these are the two guys. Is there anything you can pull out as a common factor that might make it look a little bit prettier?
X squared.
That's all I can say. And if you do that, you're going to be left with a -4x. And here you're going to be left with a 2 STU. And if I'm being a bit pernickety, I could have pulled out a 2, couldn't I? And that's as good as I can make it. Although I'm pretty sure WebAssign is pretty lenient when you're writing down these kind of answers. Any questions so far? Are we, we're quite comfortable with the chain rule process, how you go about finding partial derivatives when you have a function whose individual terms are themselves in terms of another group of variables. We good? Okay. No, I don't see anything. Oh, wait a minute. Do I want to do that? Yes, I do. I'm just looking for there's a couple of questions here I'm thinking about, but let's do this one. So here's our function. U is going to be, it's almost like they switched places. The U, the V, and the W are in terms of X, Y, and Z, or X and Y in this case. That's kind of weird. And we are being asked to find dP by dx. And we're being asked to find it when x is 0 and y is 6. So that's what makes us a little bit different from the others. Yeah, there are x's and y's here and there are UVW's, but these are just like placeholders. Couldn't I call this A, B, C and call these D, E, F? It really doesn't change the math. You just have to have that mindset where it doesn't bug you. Okay, so I want to find P with respect to X. Well, what I'm going to have to do first is that guy and then do him with respect to X. Then that guy here with V and do the V with respect to X. And then that guy W and then do dW by dx. Are you comfortable about the formula that I created from this situation? Are we good? Right, side issue. I'm going to have to differentiate this thing. I'm not going to leave it as a square root, agreed? When I have to call it a half power. So far, so good. Isn't this function symmetric? Right, I'm going to use that to help me as well. But here goes. I'll do it over here. P is equal to u squared plus v squared plus w squared to the half. The partial derivative with respect to u then is going to be 1/2 u squared plus v squared plus w squared to the power of, reduce it by 1, -1/2, times the derivative of the inside function with respect to u, which gets me 2u. The half in that guy gives me a u, and this ugly guy comes downstairs. And then to finish the whole thing off, it looks like this. Are we good? You happy with that answer? Right. So let's continue calculating this fella. I'm pretty sure I'll need every single inch of space here. Right, the derivative is u over the square root of u squared plus v squared plus w squared times the derivative of u with respect to x, which is e to the y. Because this is symmetric, can't I do dp by dv and then after that dp by dw? Can't I use those two by using this answer to help me? So when I do the second one, it's going to be just v over that square root. And the derivative of v with respect to x ends up being that fella. And then to do the last one, it's going to be w over that square root. And the derivative of this guy with respect to x. And I'm deliberately going to make a mistake here. The derivative of e to the xy with respect to x isn't just e to the xy. What's missing?
A y.
An extra y. Can you see it'd be quite easy to miss that, especially me anyway, right? So far, so good. Now, this thing is horrendously ugly, and I still haven't figured out how this is going to come into the mix, because they want to know the value of this. So that means a number, and they want to know it when x is 0 and y is 6. So I'm going to do a little kind of bit of work over here. If x is 0 and y is 6, then won't u be nothing times e to the 6, which is nothing? Won't v, which is y, times e to the nothing, be 6? And won't w, which is e to the nothing times 6, be e to the nothing, which is 1? Are you comfortable about how I found u, v, and w? Okay. Now, I know that these ugly square roots are going to be evaluated, so I might as well just do them here. That guy is going to be the square root of nothing squared, 6 squared, plus 1 squared. So that's going to be the square root of 37. Okay. Are you all comfortable about where that came from? Okay. I should be able to finish it off now, since I've got kind of the building blocks that are going to be of help. So I've got a u, which is 0 over the square root of 37 times e to the y, which is e to the 6. But really, isn't all of that just going to be 0? Now, the middle one is going to be a v, which is 6, over a square root of 37 times a y, which is 6, times an e to the nothing. Okay, that's what that one's going to be. And then I've got a w, which is 1, over the square root of 37 times e to the 0 times 6 times a 6. So let's see what we get there. That's 1. So 6 times 6 is 36. And that's 1, and that's 1, and that's 6. So that just gets me 6. So if I haven't screwed this up, isn't the answer 42 over the square root of 37? Provided I can't, I didn't make any mistakes and I can't count. I know I'm a picture straightener, but really, shouldn't you multiply the top and bottom by the square root of 37? In other words, 42 square root of 37 over 37. I know that doesn't look prettier than the original answer, but technically it's better. Although I'm 99% sure that WebAssign is generous and 42 over root 37 will be marked as correct. And to be honest, if you did that in an exam, I would still give you it as well. But it's good practice just to do things the way they should be, even if it's being pernickety. Do you know what the word pernickety means? Is it only because the context means fussy, right? Have you heard the word pernickety? It just came to me that, okay. Have you heard it anywhere except from me? Right. So nobody says, oh, my grandmother uses that word, right? Okay. I drift.
I mean, I've heard persnickety.
Well, mine is pretty close to that word. So it's probably one of those things where the Americans took what we said and then changed it because they could. Because the correct word is aluminium. Right? What did you go and do to that word? Aren't you embarrassed? Aluminum. God, what a stupid thing to do. Right? So, yeah, you probably took a good word and wasted it by sticking letters in, or most likely in Americans taking letters out. Okay, God, whatever. Right. I am now going to tell you something that we do a lot in math, but you're just going to have to accept this. Can you remember having to do in Calc 1 implicit differentiation? And judging by some of your faces, yes, you remember it, and yes, it was horrible. And we showed you a process on how to get it. And wasn't it really messy and a lot of stuff going on and really painful? It's not that we lie to you, but there's an easier way to do it. So first thing you're going to do here is you're going to take all the bits that have X's and Y's. Don't keep, the number doesn't matter. And you're going to call that f of xy. So in this case, you've got that guy. And if you want to find the derivative, right? Your good old fashioned Calc 1 dy by dx, the answer is and let's show you how you do it. If you differentiate this function, right, the top, this function here, with respect to x, you get 2xy cubed plus sine y. And if you differentiate that same function, but with respect to y, partial derivative, you get 3x squared y squared plus a cosine y times x. Oh, and don't forget to stick the negative in. I have just differentiated that horrible implicit function in less than 30 seconds. Oh, come on, is that not cool? That you could actually, way back in Calc 1, I don't know how long that would take. Would that take you about 5 minutes if you had to do it the way you did it way back in Calc 1? 5 minutes, 30 seconds, right? So you might be thinking, why didn't you tell us how to do it that way when I was in Calc 1? Well, there's a saying that goes something like, a little knowledge is a dangerous thing, right? If I had shown you that as a shortcut trick, this partial derivative thing, well, first you'd have to get your head around it. And I'm not sure I like the fact that you might have got your head around it, because wouldn't you start using it everywhere? Right? You differentiate everything as if it was partial derivatives. And that's not always a good idea, right? So that's why we kept it away from you. But now your mathematics is more mature. Do you understand that this is a partial derivative and other things in other circumstances are not, right? And that you treat one way and you treat the other a different way. But I mean, that is pretty amazing that you could do that. So let's pick an example using that. Question 11, for instance, asks us to find dy by dx for this function here. Now, essentially, all you need to do is to rearrange it so that all the variables are on one side. Don't you worry about the 9, right? But all the x's and y's are on one side. And if you do that, then the function that you're going to be using is simply just this guy. Side issue. Why do I not care about the 9? Why isn't the 9 involved in this process at all?
Because when you, it's just going to disappear anyways.
Yeah. So why bother putting it in just to make it go away, right? Basically, nailed it. That's exactly it. So if you want to find the derivative, it's negative that guy over that guy. Put a negative. All right. With respect to x, the derivative of this fella is negative sine of xy, times a y. That's busy. Put a big bracket around that then. And if you differentiate this guy with respect to x, you don't get anything. Now, if you do it with respect to y, the bottom guy gets you negative x sine of xy, and this guy gets you negative cosine of y. So there is a negative here, and there's negatives. God, there's negatives everywhere, isn't there? So if I was trying to make this pretty, I'm not sure I can make this really any prettier. Those two can cancel out. I'd probably do it that way. Just cancel the 2 on the top. You only can do it once. You're not allowed to do it to both. Yeah, that would be my best answer. Do you like that trick for finding implicit derivatives by simply just finding the capital F function and using this formula? Do you need to see another one, or are we good?
Can we see another one?
Okay, let's see who I've got. Don't have too many left. I'll do 10. Or at least one like. I don't need to do 10. These can be made up. I'll do one like 10. How about that? Okay, so I'm going to do 2x cosine of y equals x cubed plus y cubed, right? So that's the thing that we're going to find dy by dx for. So the first part of this process is to get all the x's and y's together. In this case, the whole thing's equal to 0. That means that my capital F function, the one I'm going to use in my formula, is all of this. So it's 2x cosine of y, take away x cubed, take away y cubed. And now I can get the answer. dy by dx is negative, top fella, bottom fella. Partial derivative with respect to x, you get 2 cosine y's, negative 3x squared, and that guy's 0. If you do the same function, but now you're going to do partial derivative with respect to y, 2x cosine y just turns into negative 2x sine y, because the derivative of a cosine is a negative sine. That middle term is 0, and that other term is negative 3y cubed. And I think the hardest part is figuring out what to do with that blinking negative, right? Because we've got a fraction and we've got a negative of it. I'm just going to give it to the top guy again. So it's negative 2 cosine y plus these. I'm basically thinking of that as negative 1 and just multiplying through by -1. So I get that guy on the top, and I get this guy on the bottom. Are you comfortable with that? I could have actually multiplied all the bottom by negative. It might have looked slightly nicer, but I've done it now, so I'm sticking.
Did the -3y should be -3y squared, right? Not crazy.
Don't know. I've screwed up lots of things in my life, but that there should be a square.
Okay.
I agree. There aren't that many more of these guys left, so can we call that one good? Right. Now, to finish this section off, I'm not sure we can do it, but I'll try. To finish this section off, at least, as far as I can tell, this is questions 12. What other ones have we got? Okay, we won't be able to finish it off directly, but I'll try my best to get as much done as I can. Question 12 gives you some formula to use. And the one that I'm going to do is you can use it to find that guy, dz by dx. And it's equal to negative df by dx over df by dz. Now, that formula is going to be used in this question. So we're back to partial derivatives now. So don't think of implicit anymore. So we have this function here, and I want to find the partial derivative with respect to x. And according to this, it's this formula here, although I really should put the negative in the middle, makes more sense. So the partial derivative with respect to x, you don't need to memorize that, that's given to you every time, is going to be negative the derivative of f with respect to x. Right, so what you're going to do here? Well, who do you think x is? Oh, sorry, who do you think f is? That's what I meant to say. Who do you think this f is?
Is there gonna be everything on the left-hand side of the equation?
So you're saying it's all that stuff. That makes sense, doesn't it? Seems reasonable.
I think so.
Yeah, I think so. I agree with you. So what do we get then? Well, if you differentiate all of this as f, if you differentiate it with respect to x, you get 2x. That counts as nothing, and that counts as nothing, right? So you get 2x. Now, what do you get in the bottom? Well, if you differentiate this guy here, right, with respect to z, he gets you nothing, he gets you nothing, and this guy gets you 10z. So cancel, cancel, negative x over 5z. That's actually a really simple answer, wasn't it? They only do one of them, and that's basically it, right? So it's not like you get a lot of practice at that one. Actually, I take that back. They do 2 of them, 13 as well. So now we're at the point where I am always uncomfortable because I'm not an engineer, and I fear saying something that's not right or tell you something that's not right. And then you go into your physics class and say, Mr. Robertson said you did this, and they'll laugh at me. So question 16 is an application of partial derivatives. We've actually not done anything physical that you could use them for yet. So this is, I guess, is our taster. The voltage V in a simple electric circuit is slowly decreasing as the battery wears out. The resistance R is slowly increasing as it heats up. And we are being told, as even I know, that formula. Isn't that the formula that connects voltage V, current I, and resistance R? you all seen that guy? That's probably the only equation almost everybody knows of, right? And we are being asked to find how the current is changing. So we're being asked to find how the current, that's I, is changing at a given time t. So we are being asked to find dr by dt. So far, so good. And they tell us that R is 463. And I don't know why I know this, but I do know it. Isn't that symbol ohms? God, the stuff that I must have picked up 40 years ago, because that's really the last time I did anything like that. And the current is 0.05 amps, right? The voltage is changing at the rate of negative 0.06, and that's going to be volts per second. And the resistance is changing, and it's changing at the rate that it's increasing at the rate of 0.08 ohms per second. Okay, so we're being asked to find this guy, right, using that formula, okay? And we're given this information. There's a piece of information here that's missing that we will need, and I know we'll need it because I can kind of tell essentially what's going to happen, but anyway, here goes. To find di by dt, I'm going to use the chain rule. But that formula isn't really the one I need. Don't I need to change it? Agreed? So now I'll start the chain rule. It's going to be the derivative of I with respect to v times dv by dt plus di by dr times dr by dt. Are you comfortable about the chain rule formula in this question? That's the contribution to the answer from V, and that's the other contribution to the answer from I. And we're using this guy up here. So differentiate this guy with respect to V, and all you get is 1 over R dV by dt. I'm not even going to write that down as a number yet, although it will become a number. Now, if you want to differentiate this guy here, right, with respect to R, I'm going to cut out a whole load of corners here. Wouldn't you call it that? So you could differentiate it. And can you trust me then that you get negative V over R squared? Are you comfortable that if you differentiate that, eventually it becomes that? You can check it, but you do. Finishing with dr by dt. Okay, now they want a number. That's what all this is about. So 1 over R becomes 1 over 463. dV by dt becomes negative 0.06. Well, actually, plus with a minus is a minus. V, oh, problem, over R squared times dr by dt is 0.08. We are almost there, except for one missing number. Nobody told me what V is. Agreed? How am I going to find the number, the value of V? Use this. How am I going to get the value of V?
It's I times R, so it's 0.5 times 463.
Are you all comfortable with what where that came from? You could, right? V is IR. If you tell me I and R, then I can figure out what V is happening at that snapshot in time. So 0.05 times 463, and the number I'm getting out of that is 23.15, which I'm now going to put here. And I'm only going to base it because I've got the answer over here in front of me. That is negative 0.000138. And if you want to know what the units are, it's amps per second. So this battery is very, very slowly draining its amperage. Right. Now, those people who are into, you know, electronics and electrical engineering, isn't that quite true? Because I can tell you that from a practical thing. I have an RV. Do you know if you leave your RV alone, there's a small trickle to the charge? In other words, there's a few things, even if you don't know them, right? A little light here or something, and it's sucking out the energy out of your battery. And if you leave it alone, even at that minuscule value, won't you eventually your battery go dead? And you turn up, you know, after the, you know, after the winter's by, and you go in and you look at your RV and you think, why is my battery flat? I left everything off. Aren't batteries just naturally going to dissipate some energy if you leave them alone, even if they're plugged into nothing? And essentially that's what that's telling you. So does that look practical to you? Can you see how somebody in the engineering world would say, oh yeah, I'd like to know what is going on? It's a very simple relationship. But if you can measure the information and come up with values for these twos, you can now predict anything you like. And we need a joke to finish with, so I'm going to tell a joke. Are you ready? What time should you always go to a dentist at? Tooth hurty. Christian, did you just shake your head at me? Shame on you. Okay, everybody, will you make sure that you say just your last name, please, not your full name, and you're out of here. Come on, that was a good joke, Mia, wasn't it? Even if you've heard it 10 times.
Yeah, that was pretty good.
Okay.
Professor,
Yes.
I have a question about number 7. So
Sure, I'm ready to help you. Give me a second and I'll set it up. What section are we talking about? Question 7?
yeah, this is the chain rule.
Okay, number 7. Let me find who's talking.
Yeah,
Oh, is that you? I gotcha.
Yeah, I have a question about DZ and DX. So I think there still be 2xy, but like the number 7.
Right, I'm looking at question 7. Oh, do you think I may have made a mistake in my working? Because that is very possible.
Yeah, maybe.
Okay, let me bring it up and we can look at that question again. And if I have, I'll just make sure I keep this as part of my video. Okay, so this is the question you're talking about?
Yeah, so I have a question about the DZ-DX. So I think there may be still one part about 2xy.
You're right. If I'm looking at that, isn't dz by dx going to have a plus 2xy in here?
I
agree with you. I missed that.
Thank you.
Does that help anything? It makes a big difference because the answer's still absolutely horrible, but it's actually even slightly more horrible than it was, and you will only be able to pull out an X because of that. That's a bit annoying, but I do that. 4x cubed plus 2xy, but everybody is now negative. Which means I can only pull out an X now. And that leaves me with that guy, that's an X. Yeah, that's it fixed. Any other questions?
No, thank you.
Yeah, welcome. Well done for catching that. That means you knew what the heck was going on, which is always a good thing.
I have a question.
Yes, David, what do you got?
On question 10 for 14.3, I got a wrong answer. I'm not sure why.
Okay, let me go and hunting for that. If you can hold off for a minute. Question 10 on the first one, right?
Mm-hmm.
I'm trying to bring up your particular one because you know the numbers change. Come on, there we go. There we are, 14.3. David, let's find it. W. There we go. What question number was it again?
10.
10. Right, you know, you haven't started 3. Is that because you're just thinking about it?
Yeah, I was just
Okay.
going through and looking at them and doing some of them.
Right, that's fine.
And plus
Right,
I had
so-
some of them from last semester that I had saved.
So you just need to plug in the answers, hopefully. Right. So the one that you got wrong is the first one, and it looks like you didn't do the second one because the first one was wrong, right?
Mm-hmm.
And so the function that we are going to be using is this fella here, right?
Mm-hmm.
And the way that we're going to do this guy is we're going to use essentially implicit partial differentiation, right? So I'm going to differentiate this guy, right? This fella here with respect to x. Well, normally you would say 0 here, but in implicit differentiation, we make the assumption that z, only z, is in terms of x. So this becomes e to the 8z times dz by dx. And that's going to equal, well, if you want to find the derivative of this guy, you're going to have to do a product draw because we're differentiating with respect to x. So that's going to be f dash g plus f of g dashed. Okay. So what does that get me? Well, I've got this fill again. If you differentiate this with respect to x, you get y. You leave that guy alone. You leave the first two alone and you differentiate, you just get basically that guy. Is that looking good?
Mm-hmm.
Right. Let's check on that. Let me. F dashed. If you differentiate that, yeah, we're good, right? The second one is g dashed. If you differentiate, you're going to get xy. But differentiate that, you're going to get dz by dx. There, that's the bit that I missed. So I've got this term equals that term plus that one. I'm now going to move this guy over. So I'm going to have e to the 8z dz by dx, take away xy dz by dx equals yz. This is almost identical to what you would do a way back in Calc 1 implicit differentiation. What I'm going to do now is I'm going to pull out the dz by dx guy as a common factor. And nobody mentioned that I made a mistake, which I've now just caught.
You forgot the 8.
I forgot the 8. Thank you. There. So what do you do to find dz by dx? Well, you divide both sides by this guy. Done.
Okay.
So it's a lot messier than you thought it might have been, right?
Yeah, I forgot to mess with the other z.
But there is good news. Isn't this function symmetric?
Mm-hmm.
So shouldn't you be able to make a good prediction on that answer? This answer based on that answer.
Yeah, I knew that part.
Okay. Then you are good to go there.
Thanks for your
Anything
help.
else? You're welcome. Any other
See you
questions?
tomorrow.
Oh, see you tomorrow.
Question 5 on the same section.
Okay, question 5. Ooh, I'm gonna have to do a in and out here because Dylan, that one looks to me like it's got a lot of variation that could make the answers look different each time.
Okay.
So let's find yours. Gotcha. Let's Come on, load up. It's very slow. There we go. Click on it. Right. So the function that you're dealing with, or the version of your function, is the inverse tan. So that's not a -1 power, it's actually an inverse. And I believe that's the power. Agreed?
Yep.
So let's do the first one, the partial derivative with respect to p. Right, if you differentiate an inverse tan, you get 1 over 1 plus the thing squared, right? So that's basically inverse tan of x is 1 over 1 plus x squared. That's essentially what I'm doing. Followed by the derivative of the inside function, right? The derivative of this with respect to p. Well, in this case, that just gets you q to the 9. So what I'm going to have is q to the 9 over 1 plus, if you square that guy, you get p squared q to the 18. And that's your answer.
Okay, that's the answer I got too. I don't know if I just inputted incorrectly then.
I mean, did you write that down? Or
Yeah.
you thought you wrote that down, but you didn't type it in right?
Possibly, I don't know.
Oh,
But yeah,
you
I'm looking
lost
at the
the
same
power.
answer right here.
No, you had an 8 here. That's the
Oh,
mistake. There's a 9.
whoops.
Yeah.
Oh, right, because it's just with P. Okay.
Right.
Thank you very much. I have one last small question if you have a moment.
Okay,
And
what
it's
you
just
got?
on the last question that we did today with voltage.
Yes.
How did di dv turn into 1 over r?
Oh. So we had I equals V over R, and the partial derivative of I with respect to V is 1 over R. Well, if you think about it, V is a variable. So this is a bit like somebody saying, what's the derivative of X over 3? And the answer would be just 1 over 3.
Okay, I see that.
Or you could